All right. Thank you everyone for being here today. We're 2 minutes into the hour, so I guess it would be great for us to go ahead and get started. Just a little bit about myself. My name is Ajinkya Desai, and I will be your host for today. I am a member of the student committee who assisted in organizing the California Fire Science Seminar Series. I recently graduated with my PhD in civil and environmental engineering from UC Irvine and currently work as a Lawrence postdoctoral fellow at Lawrence Livermore National Laboratory, where I study fire atmosphere interactions by instrumenting prescribed fires using ground-based remote sensing equipment primarily, and also through some eddy covariance instruments. A few acknowledgements. The California Fire Science Seminar Series is organized and supported by the California Fire Science Consortium, the Fire Research Group, the University of California, Berkeley, and the University of California at Merced. The student committee was also crucial for the success of the seminar series, and it included 12 students and postdocs from across the United States who helped select speakers and topics for the series, so credit to them as well. Just a heads up, the webinar is being recorded and will be posted to the California Fire Science Consortium website and the YouTube channel if you want to check it out after or share it with folks. At the end of today's presentation, there will be a Q&A session. However, feel free to add any questions that you have to the Q&A chat throughout the presentation, and we'll get to them at the end. Today's seminar, which is titled Wildfire Smoke, Drivers, Impacts, and Solutions, will be presented by Professor Marshall Burke. Professor Burke got his PhD in agricultural and resource economics from UC Berkeley and also has a BA in international relations from Stanford. He is quite accomplished. He is a professor of global environmental policy in the Doerr School of Sustainability at Stanford, a senior fellow at the Center on Food Security and the Environment, the Freeman Spogli Institute for International Studies, the Stanford Woods Institute for the Environment, and the Stanford Institute for Economic Policy Research. He is also a research fellow at the National Bureau of Economic Research, and his research uses tools from social and natural sciences to measure environmental change, how that change impacts society, and how society responds to that change. So, with that said, please join me in welcoming Marshall Burke.
Great, awesome. Thanks so much, Ajinka. Can
No
you hear
problem.
me all right? Sound
Yes.
okay, great. Well, it's great to be here, and happy to present some work we've been doing. I think about mainly on the wildfire smoke side, causes a lot on the consequences, thinking about health and other economic outcomes, and then trying to evaluate various solutions. Landscape scale stuff sounds like stuff Ajinka works on, related to prescribed burning, all the way down to individual level or household level interventions, trying to protect. Shot here is just one I took in the Eastern Sierras last year. You know, our California landscapes are looking increasingly like this in parts of the summer. We've gotten lucky a few summers in a row now, and maybe our memories are short. But you know, even in reasonably good years, you get plenty of days, unfortunately, that look like this. So this was, I think, August. So why are we getting more smoke? What impact is it having in the world, and what do we do about it? Is basically the focus for today. I think everyone here likely knows the overall story pretty well. We can look at trends in overall burned area in the last half century. These are steadily upwards. The amount of area burned in wildfire has doubled or tripled depending on the time scale. You know, over the last few decades. We're spending a lot of money and a lot more money to put fires out. This is the plot on the left showing federal firefighting costs. This does not include state firefighting costs. So CAL FIRE, of course, is spending a lot of money as well. State, so again, the state numbers aren't on there, but the federal numbers are up by a factor of 4 or 5, again, over the same period. So a lot more fire, a lot more money spent on fire, trying to put it out. Why is this happening? Again, to this audience, my sense is this story is probably pretty well understood. It's a combination of two sort of long-term forces. One is, but both of them are us, humans, fundamentally. On the left is a much longer time series of area burn. So I showed you from the 70s onward, and that trend is steadily up. But from about 1900 to 1970, it was again related to the suppression effort. We've been putting out fires for, in earnest for about a century now. And as we know, that's led to accumulation of fuel in our forests. And so that's part one of the problem. Part two of the problem is here on the right. We have had increasing fuel aridity driven by a warming climate. And a series of papers by Abitsoglu and Williams and co-authors have shown exponential relationships between fuel aridity measured sort of landscape-wide, forest-wide, regional fuel aridity, and wildfire-burned area. So small increases in fuel aridity leading to ever larger increases in wildfire area burned, and a very tight linkage between a warming climate and increasing fuel aridity. So a century of fire suppression giving us abundant fuels, and a warming climate drying out those fuels leads to increases in extreme wildfire activity, increases in overall wildfire activity that we've seen recently. So again, I think a pretty well understood story here. Often what we focus on when we think about the consequences of this is what we might call the direct damages. We look at structures lost in wildfires, and these also have gone up. Here our time series is not quite as long, so this is just the last 20 years. And there's a lot of year-to-year variation, but overall you can see substantial increases. 2025, my number here I think is not totally complete, but that number does include the LA wildfires. And so you see in individual years, unfortunately, in individual fires, we lose a lot of homes. In terms of direct fatalities, these are also important, but tend to be pretty small in most years, which is good. We've had some spikes in fatalities in recent fires in recent years. So here overall, the trend has been up. But one thing we'll come back to is comparing the sort of direct fatalities, people who unfortunately, and tragically lose their lives in fires, to what we might call the indirect damages, what happens from smoke and other sort of downstream consequences of wildfire, and how large are those relative to these direct damages is one thing we're interested in trying to quantify. So this will largely be a talk about air quality and its consequences. And the jumping off point, I think, here is not directly wildfires. It is, if you wind the clock back about 10 or 15 years, it's the remarkable progress we've had in improving air quality around the country. These plots show PM 2.5 trends. This is total PM 2.5, contiguous US there on the left, and then regionally you can see there on the right. And what you can see is basically around the country through about 2015, and if we could run this time series back further, we would see the same trend back to the 80s. What we saw is really steady improvements in air quality or declines in the concentrations of key pollutants. That's true across the US, it's true in the West, it's true in the Southwest, right? Just draw a line, fit a sort of linear regression with your eyes through about 2015, and those things are downward sloping everywhere. Something seems to change in the last 15 years. Starting around 2015, maybe a little bit earlier in the West and the Northwest, that trend flattens out and starts to reverse. That reversal is strongest in the West. So in the Northwest, you can see that this seems to be upward sloping now. In the West, a lot more variable. But even in the South, Ohio Valley, parts of the Northeast, this trend has totally flattened and started to reverse. And so a natural question is, what's causing this? And our question today is this wildfires? Are wildfires really precipitating this reversal in what was otherwise just a massive public policy success story, in improvements in overall air quality, driven largely by public policy, the Clean Air Act and subsequent amendments leading to improvements in air quality? So has that success stopped, and is it being reversed by recent increases in wildfire activity is one of our key questions. Okay, we're going to focus on wildfire smoke. How do you measure wildfire smoke? This is not a new question. Folks have been working on this topic for a long time. The traditional approach to measurement here has been to use transport models of various types. So from the very fancy chemical transport models to the simpler sort of Lagrangian particle tracer models, but physical or chemistry and physics-based models that take wildfire emissions and other emissions inventories as inputs, solve the complicated chemistry and physics about how particles form and how they move around in space, and then try to estimate surface level concentrations of pollutants given emissions as inputs. Our work and others has shown that those models are great for a narrow set of topics. They're certainly good for non-wildfire pollutants. They've been shown, repeatedly to be very useful tools for measuring point source pollution and the impact of point source pollution on surface concentrations. Unfortunately for wildfires, they are not a very accurate tool. And so at least off the shelf, you run Geoschem or one of the fancier transport models, and the surface concentrations you get can differ by an order of magnitude based on small changes in the emissions that you give them. And so these models are very sensitive to emissions inventories, and it turns out our emissions inventories, at least so far, are not that well constrained. There's been a lot of great recent work trying to better constrain these wildfire emissions inventories, but right now the sort of state of the science is such that there's enough uncertainty in the emissions inventories that it's not garbage in, garbage out, but the surface concentrations you get out of the CTMs are almost uncorrelated in some settings with variation in surface concentrations we see from wildfires. So we're not going to use CTMs here. We are going to use a statistical approach that tries to infer concentrations directly from a combination of what we can see from satellites and what we have on the ground from increasingly dense surface monitor networks. So these are both the official surface monitor networks, which I'll show you today, the ones that EPA maintains, so thousands of monitors around the country, as well as citizen science monitors that, in parts of the US are increasingly useful, things like Purple Air Network and other networks that measure both indoor and outdoor pollution. We're going to measure them, use them to measure indoor pollution in a way that I'll show you later on. Right now, this is focused on ambient pollution, and so the game here is to try to relate what we see from the sky to what we measure on the ground and use machine learning to help build a statistical model. What's nice about this is we can evaluate this model out of sample. We can see how well it does on surface observations that we did not train on, and so can give us a pretty good sense for the sort of the value and the accuracy of these models. Happy to go into more detail in the Q&A if folks are interested in the overall pipeline here. Part of the challenge is that, so again, our goal is to relate satellites and various other inputs. You can see our sort of stack of inputs here. We have smoke plume data. This is a data set that NOAA maintains where analysts hand annotate where the plumes, wildfire smoke plumes are. They do this multiple times per day. This is a key input for us. We have the station data, as I said. We have meteorology. We have various fire variables. We have measures of aerosol optical depth or thickness from multiple satellites or reanalysis ingestions of those. So we use MERA, which is a reanalysis, sort of a data assimilation model that uses MODIS as input, and other things about land type that previous work has shown to be useful in this sort of prediction task. But a key challenge for us is our prediction object. The thing that we're trying to predict is smoke on the ground, and particularly smoke PM2.5. But the whole problem is that's not measured, right? What we measure from the sensor is total PM2.5. And so our first task is in the ground data to try to separate what's smoke and what's not smoke. And so our approach there is actually pretty simple. What we do, and here's a given station in somewhere in California, showing a few months in 2023. What we try to do is say, okay, what's the average PM or the average background PM on non-smokes days during June and July at this given station? And then on each day, what are anomalies above or below that average? And on days when you have really high positive anomalies, do the smoke plumes tell us that there's smoke in the air? And if so, we're going to attribute high anomalies, so deviations above average for that station, that location, at that time period. High anomalies we're going to attribute to smoke if the smoke plumes tell us that there's smoke in the air. So that's imperfect, but we've done a bunch of tests that happy to talk more about. That should give us a pretty good measure at the station level of what is smoke and what is not smoke in terms of PM2.5. Again, our focus is going to be on PM2.5. So that's going to be our ground data, and then we're going to try to predict those ground data with the series of inputs that I have here. And I'll show you performance statistics here. So we have a lot of observations, and we can give you a bunch of different performance statistics. One we focus on is just the overall R squared here, which is the explained variation. How much of the variation in our outcomes, in this case station level smoke PM2.5, are explained by our inputs. And we get values of about 0.7. We push this up a little bit to about 0.75. recently, so we can explain about 3/4 of the variation in ground level day-to-day smoke PM from these satellite and related inputs. So it's not perfect, but it's pretty darn good. This is actually better than we were expecting to do. And as far as we can tell, this is sort of state of the art in terms of out of sample prediction. So these R-squareds are again from stations where we didn't train the model, we held them out of the data, and then we predicted on them and saw how well the model did when it didn't get to see that station. On the right is the station by station R-squared, sort of where we do well. We do well pretty much everywhere in the country except in the Southwest. We do pretty badly in desert areas for reasons we're still trying to understand. These areas, actually Arizona, most of these Arizona stations actually don't see that much smoke, and so we just don't have that much variation to predict, which is part of the problem. So we're still working on trying to improve our Arizona predictions. But elsewhere in California, Central California, Sierras, we do quite well. We do quite well in the Northwest, and we actually do quite well across the Midwest, which has seen a lot of smoke recently, and the Northeast. So to us, this is it's pretty good. Imperfect, but pretty good. Okay, so once you have those data, what you can do is make daily maps because you can predict everywhere. So here I'm showing you daily maps. This is a time series for 2020, which turned out to be one of the smokiest years on record in the West, in California and the rest of the West Coast. You'll see the fires start up here in July, so we're getting bad, and then August and September is when it gets quite bad. You can see, and then it will start quieting down as it starts to rain and snow in the West. So what satellites enable you to do is fill in all the gaps between stations where you didn't have data before, if you trust the model, right? And hopefully we trust the model. We've evaluated it out of sample, but now we're going to sort of take the model for a spin. So what we can do is not only produce day-to-day estimates of smoke PM, but we can aggregate over whatever time scale you want. Here are annual aggregates, so these are different maps year by year of annual average smoke PM at the sort of native resolution of the model, which is 10 kilometers, right? So this is pretty fine scale predictions. And if you want to, you can sort of blur your eyes and see that overall smoke has gotten worse. So the brighter colors, you can see the color bar here on the bottom right. The really bright colors are higher smoke PM values. So, you know, back 10, 15 years ago, we just didn't have as much smoke, right? We didn't have as much fire, we didn't have as much smoke. And that is sort of consistently gotten worse over time. We've had some quiet years. 2019 was quite quiet, very wet year around much of the West and very quiet. And since then, it hasn't been bad everywhere in every year, but it's been very bad somewhere in every year. So 2020 and 2021 were very bad in the West. We've had mostly quiet years in much of California, 2022, 2023, 2024, and including last year. So 4 reasonably quiet years in a row. For most of California, some parts of Northern California, Humboldt, have continued to be hit very, very hard, even while the rest of California has been decent. But the East Coast, unfortunately, has been hit very hard in the last few years. This is partially from fires in the US. It's mainly from fires burning in Canada. So Canadian smoke traveling thousands of miles into the Midwest, into the East Coast, leading to very, very high exposures in places that historically, as you can see on these maps, were just not that exposed to wildfire smoke. Okay, so that's these over annual trends. We can take those data, we can go back to this map and say, okay, here's the total PM. Since I know smoke PM now, I can subtract off the smoke PM and try to understand, are these overall trends in total PM, this stagnation in progress and this reversal in progress, how much of these are driven by smoke, or at least our estimates of how much smoke was in the air. So I can subtract that off. The gray area is now the smoke that I'm subtracting off. And the blue line is our best estimate of what total PM would have looked like had there not been any smoke. This would be the counterfactual without wildfires. And what you can see is in some sense good news, right? Were it not for wildfires, we would have continued to make progress. So other sources of particulate matter would have continued to go down. Good, right? Other things are still going down, but wildfires are, again, driving a larger and larger wedge between what we would have had and what we actually observed, right? And that wedge is certainly larger in the West. It's not large every year. Again, 2019 was pretty quiet. Hopefully you guys can see my mouse. 2019 was pretty quiet in the West, pretty quiet in the Rockies. But then since then, we've had some very bad years. And you can start seeing smoke showing up in the Northeast, right? The grayer wedge is really small until the last couple years, and now it's a couple micrograms, right? Which is a substantial portion of overall PM. So in the Northeast, you can see in 2024, our estimate is smoke was about 1/4 of total PM 2.5 exposure in the Northeast. And that's basically unheard of in the Northeast. Like they would never see average exposures that high, and now smoke is quite important. So is it smoke? Is smoke the cause of this stagnation and reversal? Our answer to that is yes. It is almost exclusively smoke, why we have seen these trends in total PM stop and then reverse. Okay, I'm going to talk now about the health and economic consequences. Some of this is our work, which I'll show you, some of which is work from other folks. I'll just take you through a few different outcomes just to give a flavor if folks haven't seen this evidence on just the sort of remarkably and unfortunate broad reach of smoke on a range of outcomes that we care about. So this one is interesting. Here's a bunch of plots. I won't go through all of them. Let me just give you the headline number. What these folks show is that when you get a spike in smoke in a given area, labor productivity, or how productive we are at work, actually declines. And this had previously been shown for other types of pollution. If you expose people to pollutants, they are less productive at work. That's true in quote unquote unskilled labor. It's true in skilled labor. It hurts cognition, as I'll show you in a second. So in various ways, smoke makes us less productive at work. And for each individual, these effects are fairly small. So one additional smoke day says earnings go down, or you can think of that roughly as productivity goes down by 0.1%. So one smoke day, 0.1%. Some years we get 30 smoke days or 60 smoke days, so multiply through, and these numbers start to get bigger. But this is applied across so many people getting exposed to smoke. So if you add this up across everyone exposed to smoke, you get numbers that are really, really large. So something like $125 billion in annual lost labor income, basically lower productivity due to this smoke exposure. So these are, again, small effects for each individual person, but when aggregated across the entire population and entire economy, get pretty big. We've worked on, this is with a graduate student, Jeff Wynn, we looked at test scores around the country and see something similar. We see a steady decline in test scores if you are exposed to more smoke in the months in the run-up to the test. So think of kids who have to take a test in spring. These are standardized tests, so we can compare scores over time. Basically, if you were exposed to more smoke in the academic year prior to taking that test, your test scores go down. And it's basically linear. The more smoke you're exposed to, the more your test scores go down. We can separate weekdays and weekends. Weekend smoke doesn't seem to matter much. Weekday smoke matters. So it's the smoke when you're at school, or it's the smoke when you tend to be studying during the week. The impacts here are sort of, if you try to dollarize them, I'm an economist, and so we annoyingly try to put everything into dollars. If you put these into dollars, you get something like $1 billion in lost future earnings from this reduction in test scores. You have to make a lot of assumptions to get to that number. But again, small individual effects, large effects if you aggregate across people around the country. Okay, let me talk about health outcomes now. I can't see anyone, but I want each of you to try to do the following. So I'm going to show you plots that show you on the x-axis smoke PM 2.5, basically the smoke exposure we've looked at. And on the y-axis, I'm going to show you a bunch of health outcomes. And we're going to start with emergency department visits. So how many people are showing up to the emergency department? And I want you to think in your head what this relationship looks like. What do you think it's going to look like? Like, is it going to be linear? Is it going to be sort of increasing? Is it going to be flattening out? So everyone sort of just draw in their head or in the air what they think this looks like for a second, and then I'll show you what it actually looks like. My guess is many of us are not going to get it right, because here's what it looks like. Okay, so this is, again, the effect of smoke on how many people are showing up to the emergency department. And when we first ran this, and then we ran it again, we're like, we have messed something up. This can't be right. Because what do we see? We see at low smoke levels, you see more people going to the emergency department. And then at really high smoke levels, you actually see way fewer people showing up at the emergency department on that day and over. So fewer people showing up to the ED. Okay, so what could possibly be going on? Here's what's going on. we can split it out by cause. So this is using emergency department visit data in California, where we have really sort of detailed data on cause, on who's showing up, on the zip code you came from. So we have a lot of great data. What you see is if we just look at respiratory outcomes, you see a relationship basically like you'd expect. So check out asthma here, right? So asthma is basically linear. So these are asthma ED visits. So people showing up to the emergency department with like acute asthma, right? And what you see is that's pretty linear, right? So on a pretty bad smoke day, and this is a 50 microgram smoke day. This isn't even like the worst ones that we've gotten. Like we've gotten days that are 300, right? So right now we only estimate out to 50 because we just don't have that many of those really bad days. But even up until 50, this thing is basically linear. And you get a doubling or a tripling of the number of people with asthma showing up to the ED when it's really smoking. This is what you'd expect. What do you see elsewhere though? So we can look at accidental injuries. We can look at fractures. Did I break my leg playing soccer? We can look at superficial. Did I fall down and scrape my knee or something, right? Or overall accidental injuries. So this could be things like car wrecks and sprained ankles, etc., right? These go down, and they go down pretty substantially. So why is that? Well, it's because on really smoky days, people are actually staying at home, right? Often public health officials are telling them to stay at home. Sometimes schools are closed. People are staying at home. And when they stay at home and they don't get in the car and they don't go play soccer, they actually have fewer accidental injuries. And it turns out accidental injuries are way more important for people showing up to the emergency department than respiratory causes, right? So this overall effect is driven by a combination of respiratory that goes up like this and other stuff, which mostly goes down. The other stuff, more people are showing up with the other stuff, and so the overall effect is negative. So it's sort of funny. So is this good news? You got a lot of bad respiratory outcomes, so that's clearly not good news. I showed this to some emergency department docs, and they were delighted. They were like, well, this is great. Our ED won't be as congested on really bad smoke days. But as an economist, our sort of interpretation of this is, well, what does this mean? This means like people are not getting to do the things they want to do. So sure, it looks like these injuries go down, but what this means is on normal days, we tolerate those injuries to get to do the things that we want to do. So this is actually a cost. Like this is not necessarily good news. And asthma is clearly a cost, right? So actually both of these are costs. They're just sort of, one's a very obvious cost, the other is sort of a less obvious cost. That's the weird way in which economists would think about this. The ED docs were like, no, this is all good news, which I don't know if I agree with. Nevertheless, we can look at the total effect on overall ED visits. So this is the relationship at different levels of smoke PM. But what it turns out is like we get a lot more exposure down at the low parts of this response function than we do at the high parts of this response function. We just don't have that many days out here, right? So if you sort of take the exposure weighted average of this thing, we have way more exposure up here. And so what you see is that smoke actually increases total ED visits. Why? Just because we get a lot of those low smoke days where more people are going to the ED. And so our estimates in this paper is even though on really bad days you get a decline, on moderate days you get an increase. We get a lot more moderate days, so we get a lot more total smoke caused ED visits, and those have gone up over time. Our data here stopped in 2017 just because that's when our ED data stopped. We're trying to update this analysis now. Okay, we have looked more recently, and this is work led by Minghao Chu, he was a postdoc in my group now, faculty member on the East Coast, Stony Brook. Had a paper just come out 4 or 5 months ago looking at the effects of smoke on mortality. So again, a long literature looking at total PM and its effect on mortality. Here we're focused on the smoke PM part of it, again using the smoke data that I showed you before and relating it to county data on all-cause or cause-specific mortality that we have around the US back multiple decades. So pretty detailed data from everywhere in the US on mortality. I haven't really talked about the statistical models here, but what we are really careful to do is make sure we are estimating the impact of smoke PM and not something correlated with smoke PM, right? So the whole goal is to try to come up with a causal estimate, not just an association, a causal estimate between smoke PM and some outcome. And the way we do that is, so I'm in Santa Clara County here in California. I don't want to compare Santa Clara County in California to Washington County in Arkansas where I grew up. Those counties are just totally different, right? They're different in all sorts of ways. One is in the south, it's hotter. baseline health levels are different. People eat more barbecue in the South, etc. Right? I don't really want to compare Santa Clara County to Washington County and Arkansas. Instead, I'm going to compare Santa Clara County to itself over time, mortality in Santa Clara County to itself over time as smoke fluctuates. So the comparison is take a normal non-smoky July in Palo Alto and compare it to a very smoky July in Palo Alto. Is mortality higher or lower in the year in which you get a lot more smoke relative to the year in which you didn't get more smoke? And what that sort of experiment allows us to do, again, we can't run a randomized control trial, but that's about as close as you can get to a randomized trial, right? Because whether or not Palo Alto or Santa Clara County gets smoke this year versus last year tends to be sort of random, right? It's where fires broke out, it's which way the wind was blowing that month. And so there's a lot of randomness in who is exposed. So that's the basic underlying experiment. And what you see is there's some sort of funny dips that are probably just noise in the data, but as you increase county level smoke PM, and we can do this monthly level, we can do this annual, you get basically the same pattern, you get increases in annual or monthly mortality. So, and these are pretty substantial. So this is the annual plot. If my annual exposure was high, and these are very high annual exposures, now 5 micrograms annual average exposure, that increases mortality by about 5%. Which is very large. That's a very large increase in mortality. So looking backwards, we can estimate something like, and actually this number is higher now. I needed to update the slide. It's something more like twice that now. Something like 30,000 to 40,000 deaths annually across the US annually from smoke exposure. Just 30,000 to 40,000 deaths. So again, compare that to the direct deaths that we saw before, which were on the order of 50 deaths to 100 deaths. So now we're, what is that, 3 or 4 orders of magnitude higher, 30,000 to 40,000 total deaths annually from smoke exposure based on this. So that's a lot. Again, as an economist, we sort of annoyingly put things in dollars, and this is awful for many people. Economists are like, well, it's the natural thing to do. Basically, to get this into dollars, so why would you even do that to begin with? Well, you want to compare it against other things we care about, and dollars is an easy way to compare. So again, I'm not defending this economist approach. I'm just saying what we do. You do this by multiplying by the quote-unquote value of a statistical life, which is actually a government estimated number that allows us to do cost-benefit analyses of regulations. So the current estimate of the VSL, the value of a statistical life, in the US is something like $10 million. So each individual life, of course, is priceless. A statistical life is worth about $11 million in today's dollars. And so I can multiply deaths by dollars, and I get, again, hundreds of billions of dollars in annual losses. Let's focus on the deaths, though. So 40,000 deaths annually, historically. One thing we want to understand, and what this paper did, is then try to understand, okay, we know some long-term drivers of smoke, right? One is the accumulation of fuels. The other is a warming climate. So let's just hold the fuels sort of constant, which we can come back to in Q&A. That's obviously a massive assumption. And let's continue to warm the climate. So fuel aridity continues to go up. We have a model that tells us how wildfire burned area responds to changes in fuel aridity. And we have a model that tells us how smoke responds to changes in wildfire burned area, right? So you put those two things together, and we can project forward how much smoke concentrations could change in the future as the climate continues to warm and fuels continue to dry. And what you see is pretty large increases in smoke. And these are just projections out to 2050. So here's the historical map, and here are the future maps under different warming scenarios. So this is sort of the most aggressive mitigation scenario. SSP 3.7 is the least aggressive emission scenario. It turns out by 2050, these actually don't diverge that much. These scenarios really diverge later in the century, but by 2050, which is now only, 25 years, these things are pretty close together. But what you see is there's a little bit of difference, but you see a lot more red later on here. Red here in the really dark red is like 10 micrograms. This is annual average smoke PM, so 10 micrograms is incredibly high. So if you think of background PM in much of the country being below 10 total, being like 9 or 8, this is saying in some parts of the country, smoke is going to basically double total PM, right? So really, really high values, much higher than what we observed historically. Okay, and then using that mortality function, we can then estimate, okay, how many more deaths are we going to get? And basically we get a 2x or a 80% increase in deaths by mid-century. So this is just in the next 25 years. So we calculate something like 70,000 deaths per year under future smoke compared to something like 40,000 deaths. So again, almost a twofold increase. So that's really large. That's bad news. There are a lot of assumptions based into that that sort of underlie that number, which we can talk about. But one thing to emphasize then, again, is if you monetize this, and again, the reason this is useful is because it allows you to compare to other things. One other thing we care about is other impacts of climate change. And what we can say in this paper is that if you monetize these excess deaths, the damage from those deaths, the monetized damage you get from those deaths is larger than all other estimated climate damages in the US combined. All other estimated climate damages in the US, right, combined. So wildfire smoke alone is the single most important climate threat in the US, at least by our estimates, and under this number. It's not to say we don't care about other things, but it says wildfire is really, really important. And that's important because wildfire smoke and these damages had not really been considered in policy so far. And basically what we're finding is this is a really important source of damages and really could, at least in our view, make us more interested in doing something about this problem. Okay, what can we do about it? Let me just talk about solutions really quickly for a couple slides here. So smoke is a challenge for air quality regulation. So the long-term improvements that I showed you before were substantially driven by the Clean Air Act. But the Clean Air Act does not deal well with wildfire smoke. Indeed, it exempts it directly from regulation. So if I can prove that if I'm a local air quality regulator and I can prove that a given day I had a very high reading because of wildfire smoke, I can strike that day from the record. It does not count against me in terms of whether I'm in attainment of the Clean Air Act. So wildfire smokes are exceptional events right now, and so can be exempted from regulation under the Clean Air Act. So our current regulatory apparatus that has substantially improved air quality in other contexts is not well equipped to deal with this problem. A big part of the challenge is that smoke travels pretty far, and so this is a paper we had trying to understand sort of a source receptor matrix for smoke. We estimate that if I'm in a given county, 87% of the smoke I get comes from some other county, not my own county. 60% of that comes from another state, and 12% of the total average smoke exposure in the US comes from outside the US, comes from Mexico or Canada. This was pre-2023. This number is way higher in recent years. My guess is it's north of 50% in 2023. And so this is like a really hard transboundary problem, right? Not like if smoke is coming from Canada, right, we have no domestic regulatory apparatus to deal with that very well. Let me skip this. So what can we do? Well, we know climate change is a long-run driver, so of course we can just easily stop or slow climate change, no problem there. If we fail to do that, we have some other options. One is trying to reduce fuel loading, right? The other part of the problem. And of course, I think a lot of folks probably here today work on this problem. California they're slowly getting their act together, I would say, on expanding the use of beneficial fire, prescribed fire. Of course, tribes have been doing this in California for centuries. And so I think, of course, we have a lot to learn from them on how to do this well and how to do it consistently. But California has ambitious goals of scaling this up across the state. They have not meeting those goals yet. So ambitious goals of burning 500,000 or up to 1 million acres a year. We're sort of nowhere near that. Some estimates put us around 100,000 acres now, sort of depending on how you count. So we're maybe 1/5 of the way to the $500,000 acre goal. I'll go through this quickly, but we've done some work to try to understand what sort of, if you actually expanded dramatically use of prescribed fire, what sort of benefits would you expect in terms of reduced future fire activity and specifically reduced smoke? So how much bang for the buck would you get? And of course, a key part of the problem is if we're going out and lighting fires purposefully, those are going to give us some smoke, right? So you're getting smoke with certainty for lighting prescribed fires in the hopes of getting a reduction in extreme wildfire activity later on and a reduction in smoke later on. So how do we think about that trade-off? Smoke now for sure, for a hopeful reduction in smoke in the future. So the first thing you can show is that, and part of the challenge in studying this is we just don't have a lot of prescribed fire data historically in California. This has just not been done at scale. And so what we do in this paper is the common trick of using low severity wildfire as a proxy for prescribed fire. So instead we're going to study low severity wildfire. We can talk about whether it's a good proxy or not, but it's at least a reasonable proxy. Like basically prescribed fire is trying to mimic low severity wildfire. So it's not a bad thing to look at. What we can do here is we can see, okay, if a place gets low severity wildfire, what's the reduction in burn probability over the next 10 to 15 to 20 years, right? So how much bang for your buck do you get in terms of reduced wildfire probability in a place that burned relative to a place that didn't burn? And what you see is, especially for very high severity fire, and this is measured as relative risk, and so 1 here means no difference between so it's the ratio of the burn probability in places that got burned versus didn't, right? So below 1 means the places that got burned were less likely to burn in the future. Above 1 means they're more likely to burn. So at very high severity places, you see reductions in burn probability of like 80%, and those last for nearly a decade. Again, things grow back, and by about 12, 13, 14 years, you're almost back to where you were before, but you get a solid 15 years of benefits. We go through and try to estimate, okay, taking those numbers, and then we have a separate model that relates sort of burn activity to smoke, closely related to stuff I showed you before. If we scale up to 500,000 acres a year, how much reduction in smoke are we likely to get if we did that every single year for a decade? And what we get is it depends on if you're sort of glass half full or empty. What we get is, so the experiment is I'm going to burn 500,000 acres a year every year for a decade. How much less smoke would I have gotten over the last 10 years? So if we'd started that in 2010 and run it through 2020, how much less smoke would I have gotten? And our estimates are maybe up to about 10% less smoke by 2020. So that's not nothing, right? That's a substantial decrease, but it's not like you're eliminating all smoke. And why is that? Number 1, you're emitting some smoke from prescribed fire. And number 2, you're not guaranteed to get a wildfire where you did a prescribed fire, right? So a lot of those prescribed fires you did might not end up having a wildfire sweep through, right? You might just get unlucky. So you could probably improve this number if you were better able to target prescribed fire. So this assumes sort of random targeting, which is like maybe the worst case. So our hope is with better targeting of where you do prescribed fires, you could do better here. But this is definitely an important tool in our toolbox, but this will by no means completely eliminate the smoke exposure. Let me show you one last thing that's sort of fun. We can use purple air to try to understand, okay, well, we do get smoke in the air. People have purple air monitors inside their houses. How well are we doing just protecting ourselves from smoke inside our home? So maybe we're going to get smoke outside, but if we do a good job of staying inside, maybe we're still pretty protected. What we see, at least in current data, is people are at least not consistently doing a good job of keeping smoke out of their homes. This is a hard problem. So this is the last plot I'll show you. On the top here, we have, so this is purple air monitors. These are purple air monitors now calibrated to local EPA stations, so we can do corrections for wood smoke, and you get the same answer. The top plot is outdoor purple air monitors. This is in the peninsula in California, so where I live, so Santa Clara, San Mateo County. And the bottom is indoor air monitors. So outdoor, everyone was exposed to a lot of smoke on this day. So these are 100 microgram exposure. This is a really bad smoke day. Indoors, what do you see? You see some people that have levels exactly like the outdoors. And these are people that just have their windows open, almost surely, right? So smoke's just blown in and blown out, right? So they have levels that look exactly like ambient. Other people have really low levels. My house was right here, and I was cranking all of my filters and had all my windows and doors closed, and we're at about, 15 to 20 micrograms, right? So it's not great, but it's a lot better than being outdoors. So what does this suggest? This suggests that you can improve indoor air quality, but even in places and even for households where they have purple air monitors, so they know exactly what their indoor air exposure and quality is, they're not doing a great job of keeping their indoor air quality high. And again, this is people who can afford a $200 purple air monitor, right? So how do we make this bottom map all green? And that's a really important question for me. Do we give people better information? Do we give people access and make sure they have access to indoor filtration and know when to use it. All of these things are likely important, and this is a topic that we're working on. So let me wrap up here. Wildfire smoke seems pretty bad. It's rapidly increasing. It's having a lot of large negative health impacts. These are likely to get worse rather than better unless we do a bunch of things. I showed you a couple things we can do: landscape scale, local scale. Currently, we're not doing either of them nearly enough, in my view, and both need to be scaled. If you're interested, all these smoke data are public. We have them up on this website here, Stanford Echo Lab data. I think the 2024 data aren't up there yet, so I'll make sure they're up. We should have 2025 up in the next month or so. The other thing we're trying to do is evaluate interventions, so things like giving people smoke monitors, so how well does this work to reduce smoke exposure, both in our own studies and other people's studies, and trying to have a living evidence synthesis of what actually works so we can help local, state, national policymakers make evidence-informed decisions about how to reduce these impacts. So I will stop there and look forward to your questions. Thank you.
All right. Thank you so much for that incredibly edifying presentation, Marshall. We'll open it up for questions. There are a few questions in the chat box. Feel free to keep adding them in, and I'll get to them in a bit. To start us off, there's a question by Stuart Mitchell. You're focusing on wildfire. I'll just read them out for you, Marshall. You're focusing on wildfire smoke, but urban conflagration smoke creates massive impacts to people, soils, water, and the atmosphere. How can homeowners mitigate urban conflagration smoke as it pertains to
Yeah.
toxic gases?
Yeah, exactly. No, that's a great question. Unfortunately, we're learning a lot about the answer to that question in LA. So LA is going to be an incredibly well-studied set of fires, and there's been way, way better sort of in-home and neighborhood monitoring of a sort of vast array of toxics. And so the short answer is I think we're still going to learn exactly when you get these urban incursions of wildfires, what we're exposed to and sort of what sort of mitigation works. Unfortunately, things that they've seen so far is like well after these fires, right? You get a lot of nasty stuff that settled down into the soil that gets kicked up again when we come back in and, we bring in heavy machinery to, remove damaged houses or fix up houses. That stuff is sort of resuspended in the air in a way that's almost surely really bad for health outcomes. So that was something that just had not been measured that well before, and there's a large team of folks at the UC and USC and elsewhere trying to do these measurements. There's a lot of guidance on how to go back into your home and ways to make it safer. So wiping down surfaces turns out to be really important, and there are nice resources online that sort of describe sort of a protocol of things you can do. I think that protocol is likely to be expanded in the future as we learn more, unfortunately, from the LA wildfires about the sort of long tail of exposures that we get after this. But yeah, it's a really important question.
Great, thank you. The next one is by Leila Carvalho. How do you separate in your analysis the effect of the 2020 pandemic on test scores and smoke impacts?
Yeah, that's a great question. So the way we did that is we dropped 2020 from our data. we cut the test score data off at actually 2018. COVID is a mess in basically all of these analyses. So how can you separate? And for wildfire smoke, it's a real challenge because 2020 was our smokiest year. It was also a pandemic year, right? So it's like, in some sense, a terrible year to study this stuff. So basically the ploy is always like you run an analysis and then you decide whether to include 2020. And basically the goal is to show that your analysis doesn't change whether you include it or not. In the smoke mortality that I showed you before, the estimate, you cut the data off in 2019. If we include 2020, the estimates actually get a lot larger. Now, is that confounded or meaning like, are we just somehow picking up the effect of COVID? Or other work has shown that COVID is a respiratory virus, and if you have a lot of air pollution in the air, it actually worsens respiratory outcomes, right? So it could be the interaction between wildfire smoke and COVID that actually led to more mortality. And if I had to put my money somewhere, I would put it on that. But it's exactly the right question, and the short answer is like, you never know exactly what to do, and so you try to run the analysis with and without it and like hope it doesn't change. In the mortality case it makes the estimates worse.
Thank you. The next question is, can your models distinguish? Oh, sorry, you froze for
I
a
think
second.
I lost you. Yeah, let's start
Oh,
that one again.
sorry. Can your models distinguish wildfire smoke emissions from prescribed fire smoke emissions? And or does it include both?
Um, the short answer is yes. In principle, it includes both. In I think we probably miss a bunch of prescribed fires, mainly because they just don't emit that much smoke, right? And so you don't even see it on a satellite. We depend on these plume annotations, right? And so only the really big prescribed fires do you actually get plumes annotated. Like, are the plumes large enough that you can see on satellites? So the answer is sort of like yes and no. Is that a problem? I think where we miss smoke are almost surely the prescribed fires that just didn't generate that much smoke. So that's not a perfect answer. Folks here and folks here at Stanford, or a lot of folks are trying to do better instrumentation around these prescribed fires to really try to understand what's coming off these things, how much smoke do you get, how much other stuff do you get, and that's really important because I think our analysis is pretty coarse when it comes to those sorts of measurements. So on the grounds, better instrumented prescribed fires, I think, is really important.
Thank you. When you say that monetized damages from smoke exceeds all of the other estimated climate damages in the US, what other climate hazards are you comparing smoke to?
Yeah, great question. I am comparing it to the other ones that have where damages have been very well monetized. So this is temperature-related mortality and morbidity. This is sea level rise. This is studies on labor income lost from increasing heat exposure. This is studies on crime, increases in crime as a result of temperature exposure. Some important climate exposures have not been that well quantified, so we don't have great estimates on inland flooding and the total damage on inland flooding we might get in a warmer and wetter in some parts of the world. So my claim is not that it's worse than all other climate impacts. It's worse than all other well-measured climate impacts.
Got it, thank you. And if I may, I just want to piggyback on that question on prescribed fire smoke emissions. W- What kind of prescribed fire smoke emission data would you need in order to improve emission inventories?
Ooh. Um, yeah, that's a really great question. Um, Well, let me answer a question related to it. We use the statistical approach that actually doesn't need the inventories as much. So for us, what would be great measurements is really useful measurements is like instrumented downstream measurements of PM2.5 at different distances from the fire. Right. That for us would be everything we would need to understand how a prescribed fire of a given size and given severity. Right. We can measure severity in different ways. Affects local PM 2.5. So for us, that's sort of what we need. If you want to use these as input to a transport model, then you need better inventory measurements. And Jinka, you're better situated to answer that question probably than I am.
No, I was asking because I was wondering if there's anything that we could do to instrument prescribed fires better to get to the data that you need for,
Yeah,
yeah.
100%. So knowing, yeah, knowing how the smoke disperses, and of course it's so context specific. What kind of day are you burning on? How big is the burn? Um, but yeah, so instrumenting with mobile monitors, sort of downwind of burns, it would at different distances would be the sort of ideal data set.
All right, and then maybe one by Erica. How are deaths determined to be caused by smoke? Do these decisions incorporate rare disease like ALS? Are there separate statistics for morbidity?
Yeah, great questions. So basically, no coroner or doctor is putting smoke on the death certificate, right? So we are not relying on anyone's assessment of what is a smoke related death versus a non smoke related death. What we're doing is looking at excess deaths, right? And we're saying, okay, when smoke was X micrograms, when it was 50 micrograms, how many excess deaths do we do? And excess are deaths above what you would expect for a given location in a given month, right? And then we're saying, okay, do excess deaths then go up when you get 100 micrograms? And do they go down when you get 2 micrograms, right? So we first are estimating, basically, we're estimating excess deaths and then understanding, do excess deaths change as a function of smoke? So what's nice about that is it doesn't require you to make a call on what diseases are affected by smoke or not. It just says, are we seeing more deaths than we would expect in a given location in a given day? The challenge is then it doesn't tell you, okay, these types of diseases are particularly susceptible. For that, you need a different type of analysis. And so ours is more a counting exercise. I think your question gets at, okay, like specifically who are the most vulnerable people, who should we be most worried about, and there you need sort of different data.
All right. Thank you so much. I think with that, it's time to wrap up today's session. I once again want to thank Marshall again for taking the time to share your work with us. The next presentation is scheduled for March 13th at 11 a.m., during which we'll be discussing how pyrodiversity is impacting biodiversity with Professor Morgan Tingley from UCLA. And one last reminder before we sign off, please keep an eye out for the webinar evaluation that will be sent out soon. Please fill that out. That helps us in future, while organizing future webinars. And with that, I thank you again. Look forward to seeing you in all of our future sessions, and enjoy the rest of your day.
Thanks, everybody.